Alperen.
Alperen wanted to give a talk on Fourier Transform, so we are here. We thank him and give him the scene.
Well, thanks to all of you, first of all, being here this late. And thanks to Physics Society and Scientific Communication Society for organizing these events. So we will talk about Fourier Transform. I have been in a research group researching optics and photonics for the last 4 years. And in these 4 years, I have seen many Fourier transforms, Fourier analysis. It's an amazingly useful tool. And that's why I want to give you a crash course about the subject. I will refresh the thing so that I can see my time. 1 moment. Okay. We will start by briefly knowing the guy. He's born in 1768 in France as a son of a tailor, but he gets orphaned at 9. Then he receives a mainly religious education by the Benedictine order, but he's more interested in math and becomes a mathematics teacher. In his 20s, French Revolution breaks out, and he gets more into politics and becomes friends, maybe BFFs, with Napoleon. He accompanies the invasion of Egypt with Napoleon and becomes his scientific advisor. After they kicked out of Egypt, they returned to France. He wants to work on his studies, but Napoleon kind of forces him to be a governor of some region in France. So he does that. But after a while, he's able to return to Paris and his studies. And in 1822, he publishes a paper on the analytical theory of heat, where he introduces the Fourier series, the topic of today. And in 1830, he dies. He was interested in religion, mathematics, physics, politics, bureaucracy, Egyptology, many things. He was a very versatile person. So was his method, Fourier Transform. So he develops this method to analyze the heat flow in a material. Let's say you have a metal rod, one side is hot, the other side is cold. You want to analyze how does the heat gets transferred from the hot side to the cold side. But then it is seen that we see many things in nature is explained through Fourier transform in many scientific fields, starting mainly with wave mechanics, then in quantum mechanics. And we see that Fourier transform is somewhat embroidered in the nature, as we know, but it is also a very useful tool in the digital world. Let's say in image processing, if you want to reduce noise in your image, you can use Fourier transform, or you can use it to compress your data. Also, if you're listening to music and you open the equalizer and you increase the bars for the bass lines, if you want to boost the bass, you need Fourier transform. But also, our ears utilizes Fourier transforms to analyze what we hear. So this amazing method, and this will be the outline of this talk. We will start with the mathematical basis. I will explain continuous and discrete Fourier transform, and I will show and give some examples and some insights about complex waves. This will be the part that is hardest to understand. If you don't catch this part, it's okay. You can understand the rest too. we will try to visualize Fourier transform in 1D and 2D, and I will show some mathematical operations that makes the Fourier transform useful. Then we will finish with some examples of its uses in wave mechanics, quantum mechanics, and digital world. So we got the Fourier part, but what is the transform? What is a transform? Many of you possibly haven't heard of any other transforms, but there are many. So basically, in a transform, you have this function. Let's say we have a function of time, and it looks like this. But to get more useful data, we transform it into another function with different variable. Usually, we will call this variable frequency for our cases. Fourier transform is an integral transform, which can be seen in the form like this. Our function is here inside the integral, and we multiply it with some function called kernel function, and we calculate the integral to get the transform. And this same thing can be written in discrete mathematics in this form. The underbars denotes that they are vectors. There are many other integral transforms, starting with Laplace transform. There are Hankel, Abel, Legendre, Laguerre transforms. The distinguishing thing between these transforms is the kernel function. They have the same forms, the kernel function is different. So let's analyze what is our kernel function for Fourier transform. It is in this form. If you are unfamiliar to the complex mathematics, you might be unfamiliar to this term. This thing is called as a complex wave, or I think sometimes as a phasor. So the one that I put here will show the amplitude of this wave, and the thing multiplied with I on the exponent is called the phase. And we should mention that f is the frequency and t is the time. Now we will try to understand what this function looks like. Using Euler's identity, we can write it in another notation. Maybe we can call Cartesian notation in this form. We have the real part here and imaginary part here. So this is why we call them as waves, right? We have a sinusoidal signal in the real part and another sinusoidal signal in the imaginary part. Now, before that, let's try to draw a single complex point on the complex plane. So, real values reside only on this dimension, right? On the real axis. Now we put another orthogonal axis we call imaginary axis, and we show this complex number in terms of real and imaginary values. So A here is the projection of this dot on the real axis, and B is the projection on the imaginary axis. Now, we had shown this notation, Cartesian notation. Now, let's show the other notation, amplitude and phase. So, we draw a line between the center to the dot. This is our amplitude. It is the distance between the origin and our point. And the angle we make with the real axis is called our phase. Let's take a look at that. Our amplitude is constant, 1. So whatever we do, if we change frequency or time, we will always be at one distance from the center. But our phase is a linearly increasing function. What does this lead us? Our amplitude is constant, but our phase is changing. It gives us a circle in complex domain. We start from here when phase is 0, cosine gives us 1 and sine gives us 0, we are here. And with decrease in phase, we reduce our angle and we complete a circle here. And when I write -1 here, it's our, in red, it's our frequency. 1 denotes the number of loops that we have on the complex plane. Now, in this paper, Fourier tells us that every function can be decomposed into waves. I will show it in discrete notation, but it's not very important. Let's say we have a function of t, and I show it as a vector. As you go down, time increases. So Fourier tells us that we can decompose it into waves. When I say waves, I will always mean this function. It is decomposed of waves with different frequency and different amplitude. And this amplitude is a complex amplitude which can change the phase of this as well. But it is not a function of time, that's for sure. This is called Fourier expansion or Fourier series. It is just like Taylor series. Instead of polynomials, we have waves with different frequencies. So let's open it up for a 5-element vector. We have 5 waves. They are summed together with different frequencies and different amplitudes. And let's assume that our function g is something like this. It draws a crazy pattern on the complex domain. We will, Fourier says that we can explain it as summation of these 5 waves. Let's show these 5 waves. So, let's start with the 0 term. This is a wave that is not oscillating. It's just one, but I will still call it a wave. When frequency, as you see here, it is 0, the phase is always 0, so it's just constant 1. When frequency is 1, we draw a loop in the complex domain, and this axis here tells us the number of loops on the Fourier domain. Alright? So this is basically Fourier series. And now let's look at some operations with waves and properties of these waves. We have mentioned integrals, right? It's an important part of the Fourier transform. Let's look at integral of a wave, which we are just taking time integral of a wave. It should be 0, given that if you take points on this circle and you sum them together, we will arrive to 0, because let's say this term cancels this term cancels this term. You can see that from 1 and -1 is 0. Similarly, I and -I, when we sum them, we are at 0, right? So, I have said that this integral is equal to 0. It's not always true. It's not always true for all f's. This is, if f is 0, we get a discrete value. Like I said, it's kind of a tricky thing. It's a wave that is not oscillating. We are always at 1. So our integral gives us our time window. There is a name for this function that depends on f. It's called a Dirac delta function. It has a finite value for 0 when f is 0, and it is 0 everywhere else. If our time window is infinite for, let's say, we are trying to calculate Fourier transform in continuous space and all over the space, like in quantum mechanics, we would get infinity here. Yes. And let me show you the same thing in discrete notation. here we get the number of data points and as the result. And the name of this function is Kronecker delta function, just discrete version of direct delta function. I could not mention them, but I think it will be useful for physics students in the next semesters. So, to summarize, sum of a wave or integral of a wave is a delta function. Okay, we have seen Fourier expansion, right? This is the formula from before, the Fourier series, but let's see how really does the Fourier transform work. Okay, we have this weird looking function here, and just exactly the same as before, we can expand it, right? Now, let's say, if we integrate this function on its own, or we just sum every value, we get the average of this function, right? And that average corresponds to G0 here. Because let's take the integral. Integral of waves is 0. They are collapsing at origin. This one dies, this one dies, only this one survives, and the other waves dies. So when we sum it, we get the average. Actually, this is a Fourier transform. Apparently, taking an average also is a Fourier transform.
I didn't understand why other terms vanish.
Okay, by the way, I want you to stop me just like this so that we do not propagate the mistakes. So let's say we take 4 data points in this circle. We have 1, minus I, minus 1, and I. If we sum them all together, this one and this one, when we sum them all, 1 minus 1 is 0, and I minus I is 0. And this is the same every other point in the circle. They collapse each other to the center. Is it okay now? So we get the initial element in our spectrum, the average. So the first step to make Fourier transform work is to kill the circles with summations, except one circle. This is not circle, okay. We are just killing the circles. Now, okay, we have this value, but we want to accept these other values as well, right? We have 4 other unknowns. The elements here in there. So, what can we do? We want to make them not oscillate as well. How can you make this function not oscillate? It oscillates in this direction. It has an increasing phase, right? Like this. To make it not oscillate is to multiply it with an inversely oscillating wave. Let's say this one, right? When you multiply these two functions, exponents will get summed up. This has an increasing phase, and this has a decreasing phase, and they will cancel out. Let me show you that step. We take our function, and we multiply with a -1 oscillating wave. This is the -1 wave, right? We multiply every circles with that. So this is what we get. So this was -2 oscillating, right? It was making 2 terms in the negative direction as we go. But now it makes -2 terms, -3 terms, sorry, -1 turns to -2, and now this is also oscillating with -1 frequency, and now this one doesn't oscillate. What does it mean? If we take the summation now, the only surviving term will be this. This one will also be killed. Every other circles will be killed. Only this one will survive, and we will get the first frequency in our spectrum. And we can So yeah, the second step is the shift the circles. As you can see, the constant function was here, but as we multiplied it with a wave, it shifted to the next function. So we can repeat this process for -2 wave, and this one survives. We can calculate G2 as well. And we can repeat it for with multiplying +1 frequency and +2 frequency as well. So this is, I think, the most important part of this presentation. And if you can understand this, you can basically understand why Fourier transform works. Any other questions here?
Can I have one?
Yeah.
You use 5 terms for the sake of this example, right? It's not always.
Yeah, of course. Yeah, in discrete functions, we have a vector, right? Let's say our vector has 5 elements, meaning that we have done 5 measurements in time. In that case, we need to have 5 waves. But if we have n elements, we need to have n waves to expand that data into waves. Any other questions? Yeah.
The average value of the function changes as we multiply them there, you know.
Yeah, yeah. And let's say not the average, but some of the function, when we multiply it with a wave, changes, yes. So now let me show Fourier transform again in the discrete notation. So to calculate the f frequency, we multiply our wave with an inversely oscillating frequency with f, and then we sum them, we arrive to that value, right? And this was the component here, meaning that it gives us the amplitude and phase of that wave. And if we want to go back, let's say we calculated the Fourier transform, we can take an inverse Fourier transform of the Fourier transform to arrive to the original function. And let me show you how we take inverse Fourier transform as well. So this is Fourier transform. The only difference here is we have minus in the phase here, and we have plus in the phase, and basically that's it. We make a summation based on the time domain here and frequency domain there. Okay, now we can start to visualization of our data. And let's start taking Fourier transform of some functions. Let's say we have a constant function. It doesn't change with time. What will be our Fourier spectrum? So I had shown our data instead of on complex circles in 2 different plots. So this is the real value of G changing with time, and this is the imaginary value of T. We only have a real value here as 1, and we had seen that if we sum this, we will see a peak in the 0. It's the direct delta function. It's the integral of Fourier transform, integral of the wave, the same thing. And the value that I have here is 1000, because I had used 1000 data points to plot this data, so it's gives me that. So this is our direct delta or Kronecker delta functions. If we have a wave with +1 frequency, we will have a cosine signal on the real axis and a sine signal on the imaginary axis. So f is 1 here, right? So we see a peak at not 0, but 1 in this case. I have also done color coding. As you know, when we calculate Fourier transforms, the result that we get is another complex number. It has an amplitude and also a phase. So the 1000 here represents to the amplitude. And the phase is an angular value. Now disregard these different colors here because 0 doesn't have a defined phase. So we see a peak in 1 and its phases, let's color match it, 0. Green is 0. This is again direct or Kronecker delta function, but they are shifted. And you can see it in the notation here. Kronecker delta function gives us a peak when f matches with the value next to it. So we see a peak at 1. And direct delta function gives us a peak when the argument is 0. And to make this argument 0, you need f equal to 1. So I have talked about phase. Let's take this data and apply a phase shift in this form. We said that in the exponent multiplied with I, we have our phase, right? This is also phase. This is an oscillating phase with time. This is a constant phase. Or the phase referring to when time is equal to 0. Let's look at real and imaginary axis. Now this data starts at 0, right? It is this point here. So this signal is shifted this much to arrive to this data. This is why we call it as a phase shift. We really shift this function to arrive to this. And if you remember trigonometry, this phase shift needs to have a value of pi over 2 to start at 0. Cosine pi over 2 is 0, right? And let's look at our Fourier transform. We still have a peak at 1. This thing had something, maybe I can try that. So we still have a peak at 1, but now our color changed. And our color tells us that the phase of this value here is pi over 2, which is the value we put here. Phase is quite often disregarded in Fourier transforms and makes it impossible to comprehend Fourier transforms completely. They only plot the amplitudes of the Fourier transform and they think that is enough. So if we increase the frequency to 2, so now let's count. We have 2 waves in our domain. So our frequency is 2, and we see a peak at 2. Okay. If we change the amplitude, compare the up data with the lower one, the maximum value on this one was 1. In this one, it is 1 over 2. If we change the amplitude, Fourier transform gets scaled by the same amount, which is showing some the linearity property of the Fourier transform. So now let's try something else. We have 2 waves here, and when these 2 complex waves interfere, in physics we usually call them they interfere. When we sum them, we call them interfere. So we have many unknown parameters here, right? A1, F1, Phi1, A2, F2, Phi2. Our signal is something like this. Let's say in lab, you get this data, and you know that this signal has this form, but you want to calculate what is that unknown parameters. So you take the Fourier transform, and you have something like this. So these are our unknown parameters, right? So one has higher amplitude, one has lower amplitude. For let's say A1 is larger than A2, meaning that the first wave will be here and second wave will be here. We already found A1 and A2 by looking at the amplitude. To see what is our frequencies, we can see that it is +3 and -5. And finally, looking at colors here, you can also calculate the phase of these signals as well. So this is basically why Fourier transforms used in data analysis. And if we had only first wave, we would only have this data, right? And when we add this one to the data, the Fourier transform just adds this one. Meaning that, I'm showing again linearity. If we take Fourier transform of a summation, result is summations of Fourier transforms, which makes our lives much easier. Okay, let's look at Fourier transform of a signal that we know, a cosine function. Using Euler's identity, you can write cosine function as summation of two waves, inversely oscillating two waves. And you can see that we have these twin peaks correspond with frequency peaks corresponding to the frequency of the cosine. This is similar with the sine function, but phases of these peaks are different. Okay, now let's look at two-dimensional Fourier transforms. And I will show space as our variable. Now we have a two-dimensional wave. In the exponent, we have also we have two functions as a function of x and y. You can think of this as an image. When you take Fourier transform of your image, you work in this domain. Now let's plot the wave with that has component on x dimension, but not on y dimension. So in x dimension, we have our regular cosine signal, and in imaginary dimension, we have the sine. And when we take Fourier transform, now this is another way to visualize Fourier transform. We have an image here, right? So we have a two-dimensional image here as well. In the horizontal axis, we have the horizontal frequencies, and on the vertical axis, we have vertical frequencies. We see our peak on when fx is equal to 5 and fy is equal to 0, referring to these values. And the black here means 0, and the colored dots here will mean a number with some amplitude and with some phase. So this is a two-dimensional color map. In the next years, it will be easier to understand. Let's add a pi phase to this signal. So we will show it with a red dot because pi phase is shown with red, and we have the one amplitude here. So that's how we color code it. And this is how you can show two-dimensional complex images in a single image with two-dimensional color coding. So we had this this function, this image. If we if we create the same thing in y, it's like rotating the image 90 degrees, and same thing happens to the Fourier transform as well.
And how do you rotate it? What's the difference in that expression?
Here we have X frequency, and here we have Y frequency. Yeah. I need to go a little bit faster. So if we have two frequencies, we get this result. It's like a wave going diagonally. As a break, let's and this is the artistic slide of today. Next one. Let us take a break and analyze Fourier transform of some patterns. You can think it in two ways. You can either think that this one is Fourier transform of this one, or vice versa. But what I suggest you to do is use this as the frequencies and this as the waves or the real data. So we need to have same symmetries as our frequencies, and you kind of can see it. If we have a triangle, we have a at least in amplitude data we have 6 of these lines. This is similar to the when we have an hexagon, but it is modulated as it goes, because the parallel lines we have all over the place. So if we have a circle, we get this beautiful pattern, and this is actually can be used to explain some beams that we create in the lab. It's called a Bessel beam. So this laser gives us a Gaussian beam. There are other beams that you can create, and we see this intensity pattern in the light. It's beautiful. If we fill it, we see that most of the intensity is measured at the center, and we have this star, we have this transition. So let me show you, first summarize, then show you another mathematical operations in Fourier transform. So we have talked about summation, and we have say that this is the linearity property of Fourier transform. Then there is a shifting property. This is the Fourier transform of a constant function. It gives us a peak at 0. If we multiply this one with a wave, we get peak at that frequency. So whenever we multiply our function with a wave, we will get that amount of shifting in the Fourier domain. There is another very important operation that we can talk. So this is summation and subtraction, right? But if we multiply two functions, we have a convolution of Fourier transforms. And this is a quite useful thing. Let me show you what it does. So this is how we write convolution in integral form. This is a very complicated thing. When I look at it, I don't understand anything, but it's a quite simple operation. Let's say our f is a function here. Just have 2 peaks. This is an image, 2 peaks here and here. And we want to convolve it with some function g, shown as this. And when you see the result, I think you can easily understand what convolution does. You take this function and you shift it to the, you shift it for every position, and then you sum the results. When we shift it, we only see a finite value when we are here and here. So the result is we shift this one here, plus we shift this one here, and we see that here. Usually our data is not so simple. When we have single isolated peaks, we can draw this map. Let me show you an example of convolution in microscopy. let's say you have this beautiful high resolution bacteria here, but when you image it, the thing that your microscope do can be explained as a convolution. It's like you take this beautiful image, then you convolve it with this, which blurs the image. And this is what you see with your eye on the microscope. By the way, we are at 40 minutes. This may take maybe 20 more minutes, so anyone who wants to leave can leave without any judgment.
Can I ask a question?
Of course.
Why does the effect of microscope can be explained with convolution, with a kernel?
In microscope there are, let's say, 3 operations. First, we have propagation of light. Then this light goes through an aperture that limits some of the light. Not everything can get passed through. And this aperture is usually on the form of a lens. And lens also adds a quadratic phase to the input light. Then it propagates again, etc. It's a somewhat complicated thing to show, but I'm just saying it quickly here.
Oh.
Yeah.
And also this kernel G. If my fx, y was just a delta function, then would what I get be the kernel G?
Yes, exactly. I mean, in the previous slide, it's almost exactly like you said. We only have 2 delta functions here. And let's say I block this, and we have delta function here, right? Then we would have the kernel right at that position, right?
Oh, alright. So even without going into the physics underlying it, can we deduce that the effect of microscope is like gxy because it's a linear system that commutes with translation, and it's just its impulse response.
Yes.
Oh, alright.
Mostly, yeah. Yeah, that's a nice catch. So, why do we use Fourier transforms in convolutions? We need to calculate these convolutions, but as you had seen in that integral, it's a very hard thing to do. You shift one function, multiply, shift again, multiply, shift again, sum again, etc. So this convolution property of Fourier transform tells us that instead of taking that integral, you take Fourier transform of these functions, you multiply them in Fourier domain and take inverse Fourier transform. So convolution in real domain is multiplication in Fourier domain, which is much easier to do. I wanted to include, I started the usage areas now, and I wanted to include something from my research, but I need to be fast in this part. In my research, I want to image not the amplitude, but also the phase of the light. And let's say we have waves coming like this, and also I try in here. We have parallel wavefronts propagating, and they go through some object that slows them. Like our objects were going in air, then they go through a glass that slows them, and they have this strange shape. Or that strange shape can be a bacteria. So it modulates the phase of the light. The wavefronts take copies these fronts. When I want to image in a camera, I cannot image the face. Let's explain it in Fourier domains. The black circles will always show the Fourier transform of the fields. The Fourier transform of this wave here is at the center. Let's let's say Fourier transform of that modulated wave has that shape. When it hits the camera, because of how the camera functions, we take our field and we multiply it with complex conjugate. So what camera does is a time integral. Light oscillates very quickly. Camera doesn't catch that. So we can only see the amplitude of the object, but the phase information is lost. To recover phase information, we put another light here. Let's say we put a light without going through object. It has this Fourier transform, and in the camera we have this, right? The thing you can calculate is here. I record the picture, then take the Fourier transform, and I see this pattern, right? So I will use this light along with this light, like in here. I will interfere them. Their interference look like this, and on camera, if I use this configuration, this thing will be summed with this thing, so this is not useful for me. So the trick is, I take this light and give it a bit of angle. Like, let's say this was my camera. In this case, I send the light directly, but now in this case, I send it with an angle. As you can see with blue lines here, the orientation is changed. When you change orientation of light, it changes the position on the Fourier domain. So this is the sample light, and this is the reference light. The reference light is shifted from the center because you shifted the incidence angle. And when we put it to the camera takes the time integral, etc. And we can see that, okay, the center is polluted, but at the far sides here, we have some useful objects. Those useful objects are the multiplications of this one and this one, but they are complex conjugates, etc. Let me write it here. So this thing here is sample field multiplied with complex conjugate of the reference field. So I can take this one to calculate phase of this light. And this is I know the reference light. It doesn't go through anything. This part is not important, but I can isolate only the sample light. I can calculate both its amplitude and phase. So I think some of you are excited about this stuff. Another usage that we see, or another relation of Fourier transform we see, is in quantum mechanics. It's called space momentum duality. So in quantum mechanics, we have wave functions, and they are crazy objects. They claim to know everything about a state. So this thing here, we assume that it has every information possible about the state. But to see this, let's say, if we want to see spatial properties of this state, we project it into our space here, and this gives us information about position information about our particle or state. We can do the same thing with momentum of the particle, and we see that there is a Fourier transform relationship between these two. So if we know the position of the particle very narrowly, we know exactly where the particle is. We have no idea about its momentum. It can go anywhere. And this way means that we really have no idea about what is the momentum. And vice versa. If we know the momentum precisely, we have no idea about the position of the particle. And this is just solutions that we can derive from Fourier transform. We have a wave here, and the Fourier transform is a delta function. And the thing you heard as Heisenberg uncertainty principle can be also shown in Fourier representation like this. This is less known and I think less studied, but same thing can be written about energy and the time. This has been explained to me in the following way. Let's say we have a photon in some cavity, and we want to learn about energy of this photon and when will it be emitted. These things have the same relationship. If we know the energy precisely, we don't know when it will be emitted, and if we know when it will be emitted, we don't know about the energy. Again, the uncertainty relationship. And we are nearly there. As a last example, let me show you data compression that we can do with Fourier transform. Let's say we have this beautiful image here. We take its Fourier transform, and Fourier transform is a very unequal place. Fourier domain is a very unequal place. I have shown here the square root of the modulus so that it helps us see. Sometimes logarithms are used. We see that only brightness here. So if I say that I want to send this picture to my friend, but I have a very slow internet, I'm saying to my friend that I will send you just these components, and I will give you the dimension of the original image. I will send you only these central components. Then you can calculate inverse Fourier transform and arrive to the same image. And this part here is only 1/16 of the original image, so 1/16 of the original information. So when my friend calculates the inverse Fourier transform, he gets almost exactly the same pictures. There's a small difference, but I'm sure it cannot be seen there.
Can I ask something?
Yeah.
What causes this difference?
Let me think. So when we look at a screen, we have pixels, and we want to have high resolution in our pixels, right? So the camera that recorded these pictures has many pixels, but as it turns out that waves are better, or a compact way to describe the images or patterns. Let me try again. I will give you some. I will give you my idea why that happens. If we have a random function, if we have a random and we calculate Fourier transform, we will see completely random Fourier transform as well. It will not be. It will not pollute the center. But as it turns out, that the nature has some order, I think, so that only the central components and low frequencies are polluted. Another explanation is, like I said, we want to see high number of pixels. This extends the Fourier domain, but apparently we don't need that much. Yeah, that's as far as I go.
I may have an idea, but it might be wrong.
Yeah, let's see.
The Fourier transform, eigenfunctions corresponding to Fourier transform away from the origin are those with extremely very high frequency.
Exactly.
And since most of things we have don't change extremely rapidly over small distances, they might be redundant, but I might be wrong.
Yeah, that's a quite beautiful answer. Okay. This was it.
Wait, I have
Yeah.
another question there.
Of course.
So this filtered image then, is it a bit more blurry in
Yes.
this case? Oh, all right.
Yeah. If you look closely, you can see them.
So it mostly causes problems not when there is a single color outside, not when there's a lot of single color, but mostly when there is quick changes between colors, like the sky and roof.
Yeah. It's hard to capture fast changes with components here. We need high frequency components, like you said. Yeah. We can continue with questions for like 10 minutes, but let's finish the talk officially for now. I thank you. It's always. Yes.
What is the picture in the previous slide? We done the transform, Fourier transform with a picture. What if it was a word? I mean,
Word?
Word.
Word.
Yeah, it was a word. Let's say I'm sending a message. It's in binary, maybe I don't know really. But then we take the Fourier transform, we go to the center, and then inverse. What does happen?
Depends on how you code the message, I think, matters. Because small changes here mean some amplitude changes, right? Like Alperen said, the changes on the roof and the sky is not as stark as this one. We have some amplitude modulation. But if we see modulation in your coding system and A changes to N C, so C is not close to A, but amplitude modulation is close to here. So we would have many errors in that case, or if we do not come up with a smart way to do it.
Can we talk about the Fourier transform and fractional solar spaces?
What? Fractional?
Fractional solar spaces.
I don't think we can.
Oh, all right.
Not me. Yes.
Do you have any insight into what we can't describe with waves? Are there any functions that goes beyond the power of the Fourier transform?
We can describe every function with waves as an result of linear algebra. If we have n orthogonal functions, we can describe any function with n elements. But sometimes waves are not useful. And the list I showed at the beginning, like there are many integral transforms, like Laplace, Hankel, Abel, Laguerre, Legendre. Even in light, when we describe the beam, this beam is called a Laguerre-Gaussian beam. Even we do not use Fourier transform in this case. We have orthogonal Laguerre functions, and we use Laguerre-Gaussian functions to explain this beam. So depending on the problem, Fourier transform is not always the way to go, even though sometimes I don't want to hear that.
Thank you.
I'm prepared for advanced discussions. We can continue later. Right? All right. Any other intermediate level questions? Anyone can leave, by the way, but I will stay here until you guys start leaving. So yes.
In discrete finite form, like we need n waves to calculate Fourier transform, but like what is the non-discrete?
I didn't hear the last part.
What is the non-discrete one?
In non-discrete form, let's say we have a function of space, right? Yeah, let's say in quantum mechanics, they need infinitely many ways to describe their function. Yeah, Okay, let's wrap it up. You can find me after this, okay?
Okay.